Okay, so having gone over the FIP quiz, if you have further questions or you want depth, go to YouTube. It's posted there. So what we've been talking about so far in 4A has been this idea that as long as the net force is 0, the object is not accelerating. And that's true for objects that are standing still. It's also true, and I think this is the part we haven't yet stated explicitly, that it's true for objects that are moving at constant velocity. So if you're moving along a perfectly smooth, which doesn't exist, road on perfectly smooth tires, which don't exist, then there is no acceleration. You know, frictionless surface in a vacuum, no wind resistance, no friction from the road, and you're moving at constant velocity, then, you know, there's no force required on the object, the car. I keep hitting the wrong thing. And this is the same thing that we've sort of talked about, and it's putting it together. So you have lots of forces acting on an object simultaneously, and when you take the sum of all of those, that's the net external force. And you resolve them the same way you resolve vectors. So if this is, you know, the force of an elf on a cookie, should have more cookie problems. I'm still bummed that we're not doing our box of Christmas cookies. That's okay. At some angle, we can resolve it into the force of the elf on the x and the force of the elf on the y. So okay. And this is what we started doing with the 4A problems. So did we actually get through this together? Because we did 4A. So I'm assuming that we talked about this slide. But same thing. Look at all of the forces acting on an object. Always draw your free body diagram. Always label it well. We're starting to get into the problems where you should allot an entire notebook page for a single problem. For some of them, you'll flip over. But make that drawing big enough that you can really see the detail in it, so that you can see the angle. Making your, skimping on space and making your angles tiny is the path to heartbreak and madness, because you'll flip your sine and your cosine or not read your angle correctly or something. Okay. Gesundheit. So here's where we get into the equation that many of you remembered from physical science. F equals ma. The acceleration of an object is directly proportional to the net external force acting on it, inversely proportional to its mass. Force equals mass times acceleration. In other words, the bigger it is, the more force it takes to get it to accelerate at the same rate. So, and it's net force. It's not just one force or the other. It's the net force acting on it. So if we go back to thinking about that turkey in the first problem that we considered, if this is the net force acting on this turkey, that's also the direction in which the turkey is going to move. So we didn't get to that in these problems. We're just looking at net force. But now we're going to start to be able to predict acceleration of an object based on net force. So in this case, Jason and Kaylee are going to take the turkey, and since Kaylee doesn't want any, Jason, you have a whole turkey to yourself. I hope you're willing to share. Oops. Okay. So let's look at some examples of using F equals ma. And like I said, this is where we're going to start going from just doing the net acceleration or net force to actually looking at the acceleration on the object based on that net force. And we'll start off with 4B. We'll do the sample problem together, and then I'll assign the book problems. And I do have to, before we go to that, I'll share with you this. XKCD, is a sciencey, mathy, geeky webcomic. Whoa, what happened? Where am I? Whoosh. Some great sucking noise, and then yelling but no sound, running but not able to get a grip, falling repeatedly. Huh. Looks like physics professors don't like working in frictionless vacuums after all. They're such liars. Because in physics, at the high school level and even at the beginning college level, we typically say, oh, ignoring friction or in a vacuum, because we pretend that there is no air resistance. So, ha 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 ha. Never mind. All right, let's do 4B together. So this is sample problem 4B. Roberto and Laura are studying across one another at a table. Laura slides a 2.2 kilogram book towards Roberto. If the net external force acting on the book is 2.6 newtons to the right, what is the book's acceleration? So in this case, we don't even have to figure out the net force. We're given the net force. So we're still going to draw a free body diagram because it's the right thing to do. So we know that there is a force of gravity acting on the book, and we know that that's equal to mg. We know that there is a normal force acting on the book, and since it's not sinking through the table or rising into the air, we know that's got to be equal to the negative of Fg. And we're told that there is a force, we can call it a force of Laura, 2.6 newtons that away. So what's the acceleration on the book? Well, we have F equals ma. So we're solving for acceleration. F divided by m equals a. And yes, I don't care how stupid it feels, I actually do expect you to write this and write this. Don't just plug your numbers in. I actually expect you to write the base formula, write the solve. Reason for that being, obviously they get more complicated. So 2.6 newtons divided by 2.2 kilograms should give us the acceleration. Let's do a really fast dimensional analysis here. So 2.6 newtons, what's a newton equal to? A kilogram times a meter over second squared. Very close, good. Kilogram meter per second squared over 2.2 kilograms. What does that leave us with units-wise? Hey, meters per second squared, which is acceleration. That's what we want. So that dimensional analysis piece comes in handy. And this is a simple enough problem. It's easy to do. 2.6 divided by 2.2, we get 1.181818, etc. meters per second squared. So sig figged answer would be 1.2 meters per second squared. And because acceleration is a vector, we have to have a direction. We're given right. So, we're told that this is right, this is left. So, to the right. Okay? They're not all that easy, but they're not too much harder than that. So I'm going to assign numbers 1 through 5 in the book. So this is page 138, number 1 through 5. You can get started on those. What I'm hoping to do is I will give you the worksheet tomorrow, and then you can work on those over break. I'm trying to have enough of a body of stuff that you can work on one problem a day, a simple one, a more complicated one, almost each day over break, so that you keep your skills up. Okay, get working.